Let's derive the inductor impedance. We're going to be relying on the phasor domain. So if you haven't covered the phasor domain, I recommend starting with another video or another set of videos that covers the phasor in order to understand. However, we're going to start in the time domain. In the time domain, we could have a simple circuit with a voltage and an inductor. And the voltage source could be a time-varying source. So we have this V cosine omega t plus V, and that would create a current I that is also time varying with this cosine relationship. Now, in order to apply the phasor relationship, what we know is that we want to convert this cosine into the real part of something using that Euler relationship. And that's kind of the heart of the phasor relationship. So we would be able to convert our cosine waves with the omega t dependence into this expression that contains the real part. Now, in this expression, we can see that both the two parts here, the I and the j phi, and the V and the e to the j phi, right? These don't contain the omega t part. And so we could combine those together. We could actually combine the I and the e to the j phi. We would combine those together into a phasor I, which is bold and non-italic in here, and same here. This is the phasor V. So we can make a relationship between the time-varying current and the phasor I that looks like based on this expression, and we can also do the same for the voltage. Now, we're going to use the phasor I and the phasor V to derive the impedance for the inductor. So let's keep going, and let's start from the time expression. So the relationship between the voltage and the current. This is the expression that we know in the time domain. And we're going to use these phasor expressions to get to our inductor impedance. So we're going to substitute this expression for voltage in here, and this one for current. We're going to substitute it in here. Now that we've done that, we're going to need to take the derivative of this. And so we can see that we have this e to the j omega t portion, and we know that our phasor I, right, that contains no time dependence. So this is a derivative with respect to time. So when this omega t comes out, right, we're going to have a j omega, and that's going to come down here in front. Now, looking at our expression here that we had substituted for the time varying current, we can see that the only real part of the current is this phasor I. And so we can further simplify this expression so that we have the voltage here. So we have this time varying voltage is equal to this phasor expression. And then if we take just the real part of this, we also can make another reduction. And from here, we get the voltage is equal to j omega L multiplied by the phasor I. So now we're able to convert this, right, via some substitution. We were able to convert from our time domain expression into a phasor domain expression, and we were able to apply that derivative. Now we have our relationship between voltage and current in the time domain, and our relationship between voltage and current in the phasor domain. And we can see that in the phasor domain, it's a lot more simple, right? We don't have any derivatives. So our relationship for the impedance, right, that's going to be that V over I relationship. So via rearranging, I can take the voltage divided by the current, and when I take this voltage divided by the current, I get that is equal to j omega L. Therefore, the impedance of an inductor is equal to j omega L. One more thing to note before we end this video is that when the frequency approaches infinity, we see that the impedance will approach infinity, which is an open circuit. And if the frequency approaches 0, then the impedance approaches 0, which would make this a short circuit. So thank you, and I'll see you in the next video.